So yesterday we started talking about Newton's first law, okay? And Newton's first law, as we said, governs all situations in which all the forces acting on an object are balanced. If all the forces are balanced, then we say that the net force is zero because, and this is an important term for us to know, the net force, okay, is the vector sum of all forces acting on an object. Okay, it's kind of like when you get your paycheck. Okay, if you have a part-time job or whatever, okay, you have your gross pay, which is this nice big number that you're like usually pretty happy to see, and then there's all the government extortion that comes off of that, income tax, CPP, EI, all that other junk. Okay, that all comes off of there, and then there's this much smaller depressing number that is your net pay. Net is what happens after everything has been subtracted off, where you've taken all the pluses and all the minuses and put them together. Yeah, you guys get it all back because you don't make the personal amount or being a student. Yeah, okay. Tax breaks for everybody except Joe Blow middle class. Yeah. All right. Okay, so individual forces, they only matter in terms of how they contribute to the net force. Okay, an individual force in and of itself doesn't make much difference unless it's considered to be part of the whole. All right, so if I'm looking at this situation here where I have like a book sitting on a desk, okay, so that's this one here, right? If I'm pushing, okay, the book to the left with 20 newtons, and there's, let's say, some friction of about 18 newtons resisting me, the book is going to move towards the left because there is still a net force. There's 2 newtons worth of force that is not balanced. Okay, so as a result, the book not only moves to the left, but what kind of motion will it exhibit? Is it going to move at a constant velocity or is it going to accelerate? Yeah, it's where we have to think about what we learned about Newton's first law yesterday. Newton's first law says that an object will continue to move at a constant velocity unless acted upon by an unbalanced or net force. Is there a net force here? So this object's not going to move at a constant velocity, it's going to accelerate. Okay? There is an unbalanced force that will cause it to accelerate to the left. Okay, so there's some applications of Newton's first law, okay, that we can, kind of observe in certain situations. If you had like a stack of, let's say, like checkers or poker chips or something like that, okay, and you were to flick one at the bottom of the stack, okay, you could actually knock the bottom one out of the stack and not have the stack tip over. Okay, if you did it right. I'm not saying it would happen every single time, but it should be possible to do that, okay, as long as you only exert a force on the bottom chip. So they'd have to be like fairly slippery, things like that. If there were a lot of friction, then the bottom one would exert a force on the stack and the stack would tip over. Okay, but if they were fairly slippery, you could knock the bottom one out, the stack would just fall straight down and not tip over. Okay? How many people have ever seen the trick where someone pulls the tablecloth out from under all the dishes? Okay, most of the time people just screw that one up. Okay, but it's a Newton's first law. It's an application of Newton's first law. If you're going to get the tablecloth out without moving the dishes, you don't want to exert any force on the dishes. If you do, they'll accelerate and then they break. Okay, so the key to pulling that trick off is to actually pull down on the tablecloth. Most people, when they do this trick, they grab the tablecloth like this and then they just lift it. Okay, which of course just sends a big wave through the tablecloth and tips everything over. Okay, if you want to actually pull that off, okay, you grab the tablecloth and you push it against the table, pulling downwards against the table. That way it slides out and doesn't exert a force on the dishes. Try it at home with plastic dishes. Okay, do not set the table with mom's best china. Okay, that will not go well. Okay, oddly enough, the heavier the dishes, the better it works. But okay, you want to do it with things that won't break generally. Okay, but it is an application of Newton's first law. Okay, another place where you use Newton's first law: roll of toilet paper. Okay, if you want to rip off just one square without holding the roll, okay, do you have to go really quick or do you go really slow? Okay, I want to rip off just one square, but I don't want to have to hold the roll with my hand. Okay, do I pull it really quick or do I pull it really slow? Pull it really quick. That way the tears on the perforations. If I pull really slow, I don't exert enough force to tear it, and I unroll the whole roll. Okay, but if I pull really quick, okay, then I rip the perforations and not the rest of the roll. Okay, it'd be the same as like with a box of Kleenex. Okay, if I want to get just one of these out, I pull it really fast. Okay, if I pull slow, okay, no, too heavy. It's a brand new box. It's too heavy. Okay, but with a light box, you can actually lift up the whole box if I pull slow. Okay, but if I pull really quick, it comes out really easy. Okay, kind of following me there? All right, so there's a few applications kind of that. Okay, now yesterday we were talking about what was the most important safety feature in your car. What was it? Mass. Okay, the bigger your car is, the less you are going to change your inertia, okay, or the more your inertia is going to remain the same. Okay, we talked a little bit about this formula. Oh, okay, this formula here, VF minus VI, okay, over T. The longer T is, the less A is, and A is what hurts you in a crash. Okay, related to that is this formula, mass times acceleration. That's Newton's second law. Okay? It governs what happens when there is a net force. Okay? The net force acting on an object can be calculated by multiplying mass times acceleration. So the acceleration experienced by an object is related to the force acting on it divided by its mass. The bigger m is, bigger or smaller a will be. If m is bigger, a will be smaller. Okay, so mass matters. The bigger the mass, the less the acceleration you'll experience. Okay, everybody kind of with me there? All right, I'm going to show you a couple of videos here today, kind of applications of this so you can see it in action. All right, so the whole idea here is that Newton's first law deals with those situations where there's no net force and you're just going to keep traveling at a constant velocity. Okay, even if that velocity is zero, it's still a constant velocity. So you're either staying put or you're traveling at a constant velocity, and that velocity is straight. Okay, because constant velocity is a vector quantity, so you're not turning in any way. In order to turn, you have to be able to exert a force. All right, so inertia and mass, okay? Net force can cause a bicycle to pick up speed quickly, but if I apply that same net force to something larger, like a train or something like that, then I'm not going to see very much acceleration, okay? Because the inertia of a more massive object is much greater, okay? And its tendency to continue doing what it's doing is greater than that of a smaller object, okay? So more mass means more inertia. All right, so quantitatively, the inertia of an object is measured by its mass. Okay, so again, the more massive an object, the more inertia it has. So inertia is the natural tendency of an object to remain at rest or in motion. So this is Newton's first law, okay, stated out in words. Okay, inertia is the natural tendency of an object to remain at rest or in motion, and that should be constant velocity, not constant speed, okay, along a straight line. Okay, the mass of an object is the quantitative measure of inertia. Okay, anybody need that one anymore? Yes, let's be right. Okay, so the good news about Newton's first law is there's no math to do with it. Okay, there's no formula for Newton's first law because, well, nothing's changing in Newton's first law. Everything is constant. There's no net force, there's no acceleration, the velocity is not changing, okay, all of that stuff. So it basically is just we have to understand the situations in which Newton's first law applies. Okay, those situations are when all the forces balance or there are no forces at all, which is pretty rare. Okay, Here's another application of Newton's first law. This is how your seat belts work in your car. Okay? Rather than have some complex electronic triggering mechanism that could fail if there was a power loss, okay, your seat belts work on something that cannot be refuted, and that is Newton's first law. Okay? Inside of the mechanism, okay, that makes your seat belt catch is a pendulum, a pivot point, and a locking bar. Okay? Then there's the ratcheted wheel on which your seatbelt is wrapped. Okay? Now we've all had that experience, right? When you're in a rush, you get in the car and jerk the seatbelt and it won't come out, and you're in a rush, so you jerk it again, and you get all frustrated. When you know all you need to do is just slow down, relax, okay, and pull, let it go back in a little bit, and then slowly pull it back out. Okay? But we don't do that because we're in a hurry. Okay? But it's Newton's first law that is keeping it from coming out. Okay? You jerked it really quick, and what you did is you jerked the whole mechanism enough that the locking bar locked against the ratchet on the wheel. Okay? And you have to let it back up so that the bar can go back up into its regular position. In a crash, what happens is this pendulum moves forwards because the car stops, but the pendulum keeps going according to Newton's first law. And when it moves forward, it tips up the locking bar, which catches on the seatbelt wheel and keeps the seatbelt from coming out. Okay? It'll work every single time because it relies on a law that always happens. Okay? The pendulum is going to keep moving forward. It's going to lock the bar, okay, and keep the seatbelt from coming out. Okay? That's far more reliable than the triggers used to detonate airbags, although those are pretty reliable now. Okay? They're basically an accelerometer that works similar to this. Okay? They work on something similar to what your phone uses to tell it which way you have it oriented. Okay? If you're ever like shaking your phone, you can sometimes hear that thing inside. It's called a gyro. Okay? And it just moves around, makes contact, and tells it when it's this way or that way. Okay? Same thing is used to detonate your airbag. Okay? If there's a certain amount of acceleration, that thing will move forward and close the circuit that detonates the explosive for the airbag. Okay? Airbags used to be on contact switches. Okay? When they first came out, there was a contact switch in the bumper. So if you got in an accident, the switch would get pressed against because of the impact and would detonate the airbag. Problem with that was you could detonate somebody's airbag by walking in front of their car and smashing the front of their car. Okay? There's actually a video of this guy in this like fancy Mercedes at a crosswalk, and there's this old lady in a walker, and it's taking her forever to get across the road, and he's honking at her because he's a jerk. Okay, he's honking at this poor old lady who's trying to get across the road, and she finally snaps, takes her purse and smacks against the front of the car and detonates his airbag in his face. Okay, karma sucks. Okay, that guy totally had it coming, but okay, that's one of the reasons why they don't use contact switches anymore. Okay, any impact in the right place could detonate the airbag when it shouldn't detonate. Okay, it should only detonate when there's sufficient acceleration for it to be needed. And set it off. And it's loud, isn't it? Yeah, like it's a. Oh, did it? Spider webbed it. Yeah, they detonate with a lot of force. Like it's not, like I say, it's not a pillow. It's like a punch in the face when it opens up. Okay. All right. So does that sort of make sense how that works? Okay. All right. So we're going to talk about a few examples here. Like I said, there's no problem solving to do with Newton's first law. This is mostly just about kind of how it works. Okay. But what we do need to talk about is something called free body diagrams. Okay, free body diagrams are something we're going to use in this unit that we didn't use before. Okay, so a free body diagram, we don't usually draw a picture of the object. We just represent the object with a box. Okay, in the box we write the mass of the object. Okay, let's say it's 1,000 kilograms. And then I draw from that box all the forces acting on it. So let's say that this is a car driving down the road. Okay, so gravity would be pulling on the car. Okay, the force of the road pushes back. We call that the normal force because it keeps things normal. Okay, and then there'd be the force of the engine, okay, going forward, and then there would be some air resistance and rolling friction and things like that acting backwards. All right, so I've now identified all the forces acting on the car. Okay, we've already said the car is accelerating forwards, and we can recognize that by looking at these forces. Okay, the force backwards is smaller than the force forwards, and the force up and the force down are equal. That's why the car isn't flying off the road or falling through the road. Okay, those forces are equal, they balance off. So this just helps me to identify all the forces. It doesn't help me to solve any problems. For that, I have to use a vector diagram. So now I take these forces and I put them in a vector diagram. Okay, so I would have, here's the center, here's the start. So I would have gravity, and then the normal force, so they cancel each other out. Normally I wouldn't even draw them because I know they cancel. Okay? And then I would have the force of the engine, okay, and the force of friction. All right, so I've still put all these tailed ahead. I had this first vector, then I drew the second vector, then I drew the force of the engine on the head of that one, and the force of friction back off the head of that one. All right, everyone kind of follow what I did there. All right, so now my net force is that green line. Okay, there is a net force, there's some force left over, so this object is accelerating to the right, okay, or forwards. All right, so everyone understand what we mean by free body diagram? Okay, so we draw them like this, but then in order to figure out what they add up to, okay, we have to draw a vector diagram of them. All right. You know what, these are all Newton's second law stuff, so we'll talk about Newton's second law here in just a minute.